in real life, this is what you see. In real life, this is what you see in real life. Mathematical and physically, okay? So all of you have been to your math course, the math course in 2ZZ04 or whatever, okay? You only see this part. You only see the math course. Okay, we have this, solve for it. Okay, I know how to solve physically. I know the procedure, fine, right? But I mean, you know the how to solve it. But physically, what it means is in engineering, okay, is what I highlighted. Okay, so there's a possibility that I can just give you the math. I can just give you this expression over here, right? I can give you this expression over here, right? I make you draw the structure, yes or no? Right? I can give you just this equation. I can give you this boundary condition. I want you to draw the structure. Right? Physically, what it means. So this topic is not difficult at all. Is the integration of a physical phenomenon and the mathematical expression. Is the integration. Okay? More integration than anything else. Right. So the next example I'm going to show you is how do we handle non-distributed load. Okay, can we use the same function again? Okay, can we use the same function or same approach if we have point load? Again, is it possible? Okay, so I'm going to show you another example. Okay, I'm going to show you another example.
Excuse me, Eugene.
Yes.
On the left is theta at the wall equals to 0 because it can't rotate.
Say it again.
On the left-hand side, on the cantilevered beam,
Yep.
at the wall is theta equals 0.
Yes. But I'm not taught theta yet. That's why I'm not talking about theta yet. Okay. Yeah. Right. Okay. Right. So we're gonna look at another example. Okay. So we're going to look at example. I forget which example. I think this is example number 3. So now we have a load now. We have a system now, okay? So this is a pin on a roller, right? And this is my point A. And then we have evenly distributed load. Right? And this is point B, point C, and point D, right? And this is omega Newton per meter. And then we have our respective distances. So from here to here is A. From here to here is A. And then the whole thing is equal to L. Okay. So what is so intriguing about this problem, right, is so what we're trying to find is we're going to again find the shear force and bending moment equation. Okay, I know that you don't need to use the integration method for this, but I want to show you what if we have a point load. Okay, so we're going to apply the integration using integration method. Okay, I'm not going to solve for the whole section. I'm going to solve for part of the section only. Okay, so we're going to apply we're going to apply dv over dx is equal to minus omega as a function of x. So if you see between A to B, is there a distributed load? The answer is no. What is going to happen, right? So we already know that we have V as a function of x is equal to, where we know that we have to integrate minus omega as a function of x dx plus by c1. Okay. Or if we know the limits, now if we know the limits, we don't need to get our C1 and C2, yes or no? So if we know our limits, we know that we have our V at point number 2, right? Minus by V at point number 1. So this will be equal to x1, x2, right? Minus omega as a function of x dx. Okay, we know that, right? So on the right hand side, if we know our limits, you don't need the constants. When you don't need our constants over here, you do not need to find what? Do not need the what? Boundary conditions. Okay. So the next step that we're going to do, again, we're going to integrate m as a function of x, right? So we have done this before, written this before. Or if you know the limits, right? So you have to just integrate. So the thing about this technique, right, is you have to know what is occurring the point before. Okay, you have to know the shear force, and you have to know the bending moment magnitude first. Okay, so from here we're going to find. Okay, so the first thing we have to know what is our V1, or at this stage at point A. So for this problem, we have to find the reaction at point A and point B. Okay, so find reaction at point A and point D. Okay, so for very sure we know the moment at point A is equal to 0. The moment at point D is also equal to 0. Yes or no? Right? If I were to keep A, and then if I'm going to remove D, the structure will rotate. Yes or no? The structure will rotate this way, right? So that is why moment are equal to 0 at both sides. Okay. So now we will have positive. So we do static analysis. Okay. So we will have positive is going up, summation of forces in the y is going to be equal to 0. So ay plus by dy, right? So the reaction at ay, okay, so this is ay is going up, dy is going up, and then your equivalent load over here is omega bracket. Oi, sorry, something happened. You all can't see my screen now. Hold on.
Yeah, your stream just cut off, and now we're just seeing it there.
Yep.
There we
Can you
go.
see
It's
my
back.
screen now? Okay.
Yeah, it's good.
Yeah, something weird happened. This computer is hopeless. Okay, so we're going to do static analysis. Right, so positive, that's going up, summation of forces in y is equal to 0. So we know that this is your ay. Over here, this is your dy. And your load coming down is omega L minus 2a, because the distance from here to here is L minus 2a. Okay, so from here you have ay plus by dy, right, minus by omega L minus 2a is equal to 0. And then I'm going to say note that ay is equal to dy, and the reason why this is due to symmetrical geometry and loading. Okay, so if I were to draw a line at the center, this green line, right, what is happening on the left hand side and on the right hand side in terms of load and in terms of forces are the same. Okay, so from here we're going to solve. So 2ay is equal to omega L minus 2a. So ay is equal to omega L minus 2a divided by 2. And this is also equal to dy. Okay. So we have to find now, okay. So we're going to develop what we call piecewise equation. Okay, we're going to develop what is piecewise equation. So we're going to look at, these are the points that we actually need. So we're going to divide into sections. Okay, so we have point A, right? So we divide the section based on the loads. Okay, if there's a new load, we have to divide it. Okay, or support. So point A, this is because we have our point, we have our reaction at A. Then we have to do between point A to point B. Okay, so point A to point B. Let me see, can I'll copy the diagram. I do apologize. This is not really good. Okay, so there's point A, right? So point A to point, so point A, we have a point load. A to B, right, is there's no load. And then at point B, right, we are going to have an introduction of our distributed load. Then point B to point C. Then we have point C, right? Point C is where the distributed load disappear. Point C to point D, and then finally point D. Okay. Then we can put in our limits. Okay. Then we can have our limits. So our limits over here is 0, right? A to B is 0, X to A. Because it's between A to B, B is at the X distance is A, B to C, A, X, L minus A. At C is L minus A. C to D is L minus A, X, and to L. And point D, the distance is L. Okay, so we're going to form a table. So on this table, what we're going to form is we are going to have both our shear force as a function of X, and we are going to have our bending moment. So it's a table. M, let me move this away. Okay, so we're going to have M as a function of X. Okay, so now let's look at point A now. Okay, let's look at point A now. Okay, let's look at point A. So again, we're going to apply the integration method. I repeat again, we're going to apply the integration method. So point A is just a point, right? So point A is just a point. So we're going to look at point A. At point A, the X is equal to what? 0, like what we have identified before. The X is 0. So we're going to use the integration method. We know that dV over dx is equal to minus omega as a function of x. And at point A, what you see, we have a what? Point load. Right? We have a point load. And so this will be equal to 0. Okay? So we have